Hello everyone, my name is Tabatabaee. I'm going to present to you One Bad Apple Spoils the Bunch, Transaction Denial of Service in MimbleWimble Blockchains, authored by myself, Charlene, Dr. Ivan Beschastnikh, and Dr. Chen Feng. Similar to other financial systems, blockchain-based digital currencies are concerned with privacy. Two important types of privacy that blockchain systems care about are transaction source privacy and transaction content privacy. Bitcoin, which is the most prominent blockchain system, has been shown to be susceptible to attacks against both of these types of privacy, and other protocols such as Dandelion++, MimbleWimble, and several others have been introduced to improve these types of privacy in blockchain systems. Dandelion++ is a transaction relay protocol based on a preceding proposal called Dandelion. With Dandelion++, transactions are relayed in two phases. The first one is called stem phase, and in that phase, when each node receives a transaction, it passes the transaction to only one of its neighbors. The second phase is called fluff phase, which is kind of similar to the diffusion protocol that we have in Bitcoin. And in this phase, each node, when receives a transaction, it passes the transaction to all of its neighbors except the one that initially sent the transaction. So compared to diffusion that we have in Bitcoin, with Dandelion++, adversarial nodes have less chance of receiving the transaction directly from the source, because at the beginning we have the stem phase where each node passes the transaction only to one of its neighbors, and therefore it's more difficult for adversary to localize the source of the transaction. So this figure illustrates how transaction relay in Dandelion++ works. So at the beginning, the transaction is in node source, and the transaction is passed through stem path, which is shown by green arrows, and then it reaches a node that starts the fluff phase, and in that phase, as you see with the orange arrows, each node passes the transaction to all of its neighbors except the one that initially sent the transaction. Now I will provide some background on the MimbleWimble cryptocurrency protocol. This protocol uses encryption and aggregation to enhance the content privacy of transactions. Compared to other cryptocurrency protocols such as Bitcoin, MimbleWimble has several advantages. One is that the amounts of inputs and outputs in transactions are encrypted. Also, aggregation of transactions make it difficult to link the inputs and outputs. And MimbleWimble uses cut-through mechanism, which causes the size of the blockchain to be substantially reduced because of the deletion of spent outputs. And by that, MimbleWimble achieves a great scalability, which is one of its most important features. Now I'm going to describe confidential transactions in MimbleWimble. Instead of obvious amounts, the commitments of inputs and outputs are put into transactions. So commitments are in the form that you can see. C is equal to R times G plus V times H, where C is a Pedersen commitment, V is the amount of that input or output, R is a secret random blinding key, which should be only known to the owner, and G and H are fixed ECC group generators known to everyone in the network. So the owner of a set of outputs is someone who knows the sum of the R values of their commitments. Each transaction contains at least one kernel, which is a non-spendable commitment with zero amount. So kernel has only the value r times g, because v, which is the amount for it, is equal to 0. And for every transaction to be valid, the sum of commitments in that transaction should amount to 0. So now we can see how the aggregation of transactions in MimbleWimble work. In this figure, we can see that we have like two valid transactions. So that means the sum of commitments in both of these transactions are 0. So if we combine these two transactions, the total sum of commitments between commitments in both transactions will still be 0, which means that the aggregated transaction also has the necessary feature to be valid. And we can say the same thing about all the transactions in a block. So the sum of commitments in each of those transactions is 0. Therefore, if we combine all those transactions, the sum of commitments in the resulting transaction would also be 0, which means that a block in MimbleWimble blockchain can be interpreted as an aggregated transaction. We can also observe that the sum of all commitments in the blockchain is 0. So now if we remove a spent output and its corresponding input from the blockchain, the sum of the commitments would still be 0. For example, if in the figure that illustrates how the cut-through mechanism works, if we remove output A with its corresponding input A, the sum of commitments will still be 0. So if we remove all the spent outputs and all of their corresponding inputs from the blockchain, the sum of all commitments in the blockchain will still be 0. And that is what allows the deletion of commitments from the MimbleWimble blockchain, and helps MimbleWimble blockchain to achieve a good scalability through this cut-through mechanism. Two major implementations of MimbleWimble are Green and Beam. And Beam is the implementation that we are going to use for our experiments in this research. Although the original proposal for MimbleWimble didn't specify any specific transaction relay protocol, both of the aforementioned cryptocurrency protocols have used Dandelion++, where transactions are aggregated in the stem phase. So in this research project, we designed a new type of attack against MimbleWimble blockchain that we call transaction denial of service with aggregations. We implemented and validated this attack on Beam network using a private test network and a network simulator. We find that by controlling only 10% of the nodes in the network, the adversary can prevent more than 45% of all transactions from ending up in the blockchain. Now I'm going to describe the threat model that we used for the attack. So the adversary can create nodes and connect to other nodes in the peer-to-peer network. Adversarial nodes can store and analyze all the information that they receive about transactions on the network. The adversary, although, is unaware of the exact topology of the network, but can obtain partial information through the data that it receives from the network and through the nodes that it is connected to in the network. The adversary cannot decrypt commitments in transactions to learn their amounts or secret binding keys. The adversary cannot spend outputs that are owned by others, and it cannot trick honest nodes into accepting invalid transactions. Instead of targeting specific nodes or users, the adversary is interested in mass attack on the honest portion of the network. The adversary can deviate from the relay policy of the network and disregard the relay phase of transactions. And the adversarial nodes can generate new valid transactions. So now I'm going to describe the design for the attack. Each transaction can be recorded in the blockchain only once. So among different aggregations that have one transaction in common, at most one of those aggregations can end up in the blockchain. So we designed the attack as follows. Let TA be a new stem transaction received by an adversarial node. The adversarial node generates a new transaction TB, and the adversarial node fluffs the aggregation of TA and TB and also TB itself. Because TA is fluffed as part of an aggregation, other nodes in the stem path of TA, which have also received TA before, will not separately fluff TA. Now, if the adversarial node creates TB such that miners prioritize TB over the aggregation of TA and TB, then TB will end up in the blockchain, and because of that, the aggregation of TA and TB cannot end up in the blockchain because it has TB in common with another transaction that has already ended up in the blockchain. And therefore, TA will not end up in the blockchain. And therefore, with this approach, the adversarial node can prevent transaction TA from ending up in the blockchain. We have provided a simulation of the beam network to estimate the percentage of stem paths that the adversary will be incident on given different network variables, such as the percentage of adversarial nodes. To implement our proposed attack, we modified the source code of Beam in the testnet branch, and to validate our proposed attack, we have implemented a private test network using Azure Virtual Machines. We have launched 100 virtual nodes in 2 geographically separated servers located in the eastern United States and Southeast Asia, with each server containing 50 virtual nodes. In our private test network, we used a fake mining scheme to avoid wasting our resources on the expensive process of proof-of-work mining. For evaluation, we have focused on how does maliciously aggregating a transaction with other transactions increase the transaction processing time from the user's perspective. To answer this question, we need to first determine the proportion of transactions that can be attacked by adversarial nodes, and second, the impact of our proposed attack on a targeted transaction. To estimate the proportion of transactions that the adversary can attack, we use our network simulators. We know that the adversary can perform the proposed attack on a transaction if and only if an adversarial node is on the stem path of that transaction. Therefore, we need to estimate the percentage of infected stem paths by adversarial nodes given different network variables. So in the figure, we can see that by increasing the probability of transitioning to the fluff phase in each step of transaction relay, the percentage of infected stem paths decreases. Also, by increasing the percentage of malicious nodes in the network, the percentage of infected stem paths increases. And for example, we see that with the fluff probability of 0.1, which is the exact fluff probability that is used in the Beam network, if 10% of the nodes are malicious, the adversary will be incident on the stem path of more than 45% of all transactions. And therefore, the adversary can attack more than 45% of all transactions. To determine the impact of our attack, we have run a rogue node in our private test network that performs the attack exactly as was described in the design of the attack. And our rogue node successfully prevented all of the incoming transactions from ending up in the blockchain. So based on the results that we have from the network simulator, we know that if 10% of the nodes in the network are malicious, then the adversary can successfully attack more than 45% of all transactions and prevent all of them from ending up in the blockchain. The mitigation to our attack can be achieved by modifying the wallet source code for every node to resend the previously broadcasted transactions that haven't ended up in the blockchain. But we need to note that resending a transaction too frequently could itself cause that transaction to appear in multiple aggregations, and therefore preventing some other transactions from ending up in the blockchain. The mitigation can also be investigated in scoring schemes where each node keeps an estimate of the reliability of each of its neighbors and make routing decisions based on those estimates. Also, we can modify the protocol itself and disallow aggregation of transactions during the relay phase. And for example, only allow aggregation when transactions are being mined into blocks. Besides the denial of service attack that we described in the paper, we have designed and validated two other attacks against MimbleWimble blockchains. The first one is improved transaction source detection, in which the adversary uses information obtained from the content of incoming stem transactions for the improved detection of their sources. In the second attack, which is called delaying transaction relay, to increase the latency of incoming transactions, the adversary adds excessive delay before forwarding stem transactions. As for conclusion, we propose the transaction denial of service with aggregations on the implementation of MimbleWimble in Beam. We implemented this attack in a private test network of 100 Beam nodes and validated it. And we found that if 10% of all the nodes in the network are malicious, the adversary can prevent more than 45% of all transactions from ending up in the blockchain. Thank you everyone for attending this presentation. Please let me know if you have